Good afternoon. This is Professor Higdon. I'm here today to give you a brief overview of the research going on in my research group. I will mention first and foremost that I will not be taking on any new graduate students this fall. Therefore, what we like to do in the department is to give you a brief overview of the activities going on in the department, even if there's no one particularly going to join my group this year. So let me begin by giving you a brief overview of some of the activities, the things that we're working on in our research. Basically, my research deals with the subject of geophysical fluid flows involving the dynamics of meandering rivers, as well as large-scale computational modeling for reservoir modeling for the petroleum industry. These are the main two topics that we deal with. The idea of dynamics of meandering rivers is something anyone who's looked out the window of an airplane should be familiar with. If you look out the window of the airplane, you see that rivers often do not form a nice straight line across the field of view, but instead there are all these different meanders which occur. Not only is this the meandering that you see for the pattern of the main channel of the river, but you can see in the background here these lighter colored traces, or down here, you can see the older courses of the river which have since been abandoned, but still leave their impact on the landscape. This is an interesting slide showing you the Mississippi River. This was produced by the U.S. Geological Survey back in 1944. And basically what we're seeing here is right near southern Illinois, the Concord, where the Ohio River merges with the Missouri River to form the Mississippi River. And basically the white channels here show you the present course of the river, or at least in 1944. And these different color traces show you where the river was over the last 500 years or so. These are abandoned courses for which the water is no longer flowing, and they could be compared with those light traces we saw in that previous picture from Google Maps. One of the most interesting things is that these rivers are in a constant position of depositing sediment and hence building up the land mass. Over periods of hundreds of years, they build up short, shallow layers of land, but over the course of 10,000s of years, they can build up thousands of feet of different sediment, forming both the landform and the rocks, which may be buried beneath the surface, which form our oil reservoirs today. The interesting feature is that all these meandering, by the way, this is approximately 25 miles or so across this width of these meanders. Over time, as these rivers are meandering back and forth, they're constantly depositing soil, as we noted. And the important thing is that as these rivers meander back and forth, the soil they deposit has a great impact on the soils that we observe today. So this was the course of the river over the last 500 years or so. It's interesting to go to Google Maps. If we look at a recent photo from, say, 2016, we can see, ignore the little rectangles, that's just modern farming. But the variations in green are associated with the vegetation growing, and that's strongly induced by the types of soil which have been left behind by the rivers. If you look at, say, this circle, this dark green pattern here, you can see, in fact, that this blue channel, which was abandoned, this was back in 1765. This is what the river looked like in 1765. You can trace out this blue pattern almost exactly in terms of this vegetation. And that just goes to show that if we're interested in the top layers of soil which have formed in the last, say, 250 years, that what we're seeing is the effect of all that deposition. So we have to look at where the river was over these last several hundred years in order to be able to predict what the soils are going to look like today. And so my research group has been focused on what is the dynamics that causes this meandering pattern. The basic physics is just that if you have river flowing in a channel, if the velocity is higher toward the outside of a bend, that bend will be eroded faster and will dump sand on the inside of the bend, causing meanders to grow. And what you find is whether the outside velocity is larger or the inside velocity is larger is a major consequence of three-dimensional, complicated motions associated with what was happening both upstream from the bend and the dynamics of the bend itself. What I'd like to do is not give you a detailed explanation of the physics today, but just look at one example of what some of our simulations would predict in the simplest asymptotic model. If we imagine that we carved a perfectly straight channel and had water flowing in the channel, and we introduced an infinitesimal perturbation, we can ask how would the meanders grow? And this just gives you a brief idea. You see there's the meanders are starting to grow, and as they grow, they continue to get larger and larger. Anytime a river touches a previous meander, water will always find its way downhill in the fastest possible direction, and so old meanders are pinched off or abandoned, much as we saw in that first picture. And so this just shows you that even our simplest one-dimensional model can give pretty good predictions for the types of patterns that we saw in that example of the Mississippi River. So this is one aspect of meandering river dynamics that my students and I have worked on. Samantha Weiss, there's a recent publication in the Journal of Fluid Mechanics documenting some of the theory that went into these simulations. Next, we want to talk briefly about petroleum reservoirs. That meandering pattern I showed you, you saw how complex those meanders were, and therefore the deposition patterns were very complex. As that builds up layers of sediment which form the landforms and the rock, which eventually becomes buried as a petroleum reservoir, that gives us an incredibly homogeneous distribution of permeability and soil porosity to form the reservoir. This is giving you one example of a view of what it might look like. If you notice in red lines here, I've identified those sedimentation layers, but you can see they're not all just perfectly parallel to the horizontal. By various earth forms like earthquakes, shear bands, things of that nature, these red sedimentation layers have been broken up into regions at all sorts of different angles. That is a process which forms what we call reservoir rock, which contains the oil that we recover from the ground. This just to give you a quick idea, if you look at what's called an outcropping, where a chunk of rock has been exposed by these various geological forces, you can see here indeed the extreme heterogeneity in terms of the layers which have been deposited. In my group, we are interested in looking at what happens when we have multi-phase flow, oil-water basically mixtures, through these porous rocks which are incredibly non-homogeneous. And one of the things I'm just illustrating here is a typical situation where what you have is a reservoir. In this case, I draw it as a square chunk of area, might be about 10 kilometers on the side. Here we're looking at a top view. We're up in the sky, we're looking down at the earth, and we're saying if the reservoir is about 1 kilometer by 1 kilometer, and there's a patch in it, and the reservoir, by the way, the depth of the reservoir is only about 100 meters, but that 100 meters may be located kilometers below ground. Here we're looking at something we're saying, okay, you have essentially homogeneous permeability through most of the material, but there's some rock formation here which is impermeable in the shape of this little rectangle. We're showing red where oil is originally saturating most of the reservoir to say 90% oil. And now we're going to inject in the bottom left-hand corner here, we're going to inject water, which will be shown in blue. That water is going to push through the reservoir and eventually be pumped out near the top. So what we can see happening is, there we have it. You see the water is pouring out. It's mixing with the oil to give those intermediate green and yellow colors, but you can see it cannot penetrate this region of impermeable rock up there in the center, but that it does indeed still move around that rock and pretty much push out most of the oil in the reservoir. Note that when the green color reaches this top corner, that says that the water we've pushed into the reservoir is pretty much now pushed out as much of the red oil as it can, and now you have water in and mostly water out. That's called breakthrough, and that would represent the effective end of the reservoir simulation. Here's another example where we have, again, essentially a homogeneous porous medium, but in this case, this dotted black line represents a very highly permeable sandstone channel. And we're going to see that that could have a dramatic effect on what happens when you try to inject water down here. So we're injecting water to try to push out the oil. It's now proceeding in a perfectly uniform fashion. But once that water hits that sandstone channel, sandstone is so highly permeable, it acts like a superhighway. And with that superhighway, the water was able to charge up that low permeability channel and leave most of this oil behind. You get what we would call premature breakthrough, and that means that it would be very difficult to use this secondary oil recovery of pumping water through this particular reservoir. So these are just two quick examples to show by the way, these are very high performance, very challenging computational simulations, but it shows you what we look for in doing reservoir simulations in the oil industry. Number one, if we know the geometry, we use simulations like this to try to predict how the oil would be forced out by injecting water. Secondly, by comparing notes with our guess for the geometry to what we actually observe from some petroleum tests, we can say, we didn't quite have the geometry right, and it becomes what is called an inverse problem. Try to figure out what the geometry was to match the observed pattern of oil displacement. So, in a nutshell, then, that gives you a really quick overview of what we do in my research group. I thank you for listening this afternoon, and I have this up on YouTube where you can watch this at whatever pace you would like. So thank you for your attention, and have a good day.